We'll start with some announcements. So we all know. We have an exam on Friday. So we have an exam on Friday, we have a homework due Wednesday. I'm planning to do a review session in class on Thursday. And that review session is going to be looking at you. Unless you have good questions for me, I don't come with any content prepared. So, especially in a class that's this small, please come with 4 to 5 of the most challenging questions. Something you'd like to have additional practice with. What was the most difficult aspect on that study guide? Most difficult couple of things just that you'd like to see an extra example of. If you'd like me to generate examples before class, which can be useful, that way the examples aren't just the first thing that pops into my mind. It's something where that actually has educational value, where I can find an example that has a particular quality to it that might be part of your question. Then send me that ahead of Thursday's class so that I can compare it. And preferably not Thursday at 8:30, because that doesn't give me enough time to prepare it. Questions about this week? All right, we are barreling down just a couple of shorter units, I guess I could call them. I guess this is really embedded in one regular languages unit, but a couple of short aspects of that before we hit our first really big major proof type that we're going to be covering in the class, which is a major sticking point, and we will probably be on that for quite some time, just getting some repetition, getting practice with it, making it as intuitive as we possibly can before we move on from that. But the first of those is going to be regular expressions. And this is a very fun topic because it actually has applicability to most computer sciences every day. So who's messed with regular expressions in some capacity? 1.5 people? Excellent. So let's start by saying that so far we've looked at in detail one way of expressing or describing regular languages. We've looked at finite state machines. Well, finite state acceptors. We looked at the DFA and the NFA, but there are other ways to also describe regular languages, and we can show that all of these are equivalent to each other. So if you could construct a DFA for a language, that language is regular. If you can construct a DFA for a language, then you can also construct an NFA for it. If you can construct an NFA, then you can also construct a DFA. So there's equivalence between DFAs and NFAs. We will find that there are also equivalences between DFAs and regular expressions and regular grammars. So those are the two things that we're going to be covering next. So one of those other ways is regular expressions, and it is just an expression. So what can be part of a regular expression? Now note that if you have seen regular expressions before, you've probably seen some way to express them that is based on the English alphabet and the English language. So we strip that away when we don't know what language we are covering. So we don't have things like brackets, where if you've seen them before, you have something like bracket A-Z that says any character between A and Z. So all we can use in general in this class are strings or symbols that consist of characters in the alphabet. We can use parentheses to show groupings. We can use operators So it looks very much like a math expression, but instead of having our typical math operators, we have plus denoting a union. It does not mean add, it means union. Or you can also think of it as concatenation, that's not quite. The star denotes concatenation. So a union is your or, your concatenation is your and, or your, these need to appear together. If you have a superscript star, then we have star closure, which means 0 or more repetitions of the sub-expression that comes before it. If there's just a single character star, that says there can be 0 or more of that character. If you are star closuring the something in parentheses before that, that's that entire expression, sub-expression repeated 0 or more times. You can also have a superscript plus that isn't here that represents the positive closure, saying that that needs to happen 1 or more times. It's not absolutely necessary to do a positive closure. So this is all that is absolutely necessary. If you had a positive closure, how could you rewrite that in terms of just the plus, the dot, or the superscript star? So for instance, I have a sub-expression that is AB plus. This says that we're going to have 1 or more repetitions of the substring AB. How could we rewrite AB plus using just these 3 things? Yeah. AB, AB, sorry. So this just ends up being a shorthand of that, and note that if I omit the dot for the concatenation, it's still there. So we don't have to have A dot B dot parentheses A dot B star. Anything that's just concatenated is concatenation. Absolutely right. But we allow that plus just to have shorthands. But in general, everything can be written just using those 3. Has applications outside of just computer science theory. If you ever want to open up a browser or a text editor of some kind, text editors have this feature built directly into them. So if you open up a, I don't know, what text editor do people use these days? Yeah, Word allows it, Notepad++ allows it, VS Code allows it, Vim allows it, whatever people use, Emacs allows it. So you just type in a regular expression. No, it's not exactly the same regular expression language as this, but if you learn the English regular expression language, then you can type that in and it allows you to search like this. So I could search for instance, all zip codes by looking for 5 digits in a row. And I could look for the extended ones if I said five digits in a row, followed by a dash, followed by 4 more digits in a row. So you could look and search for that particular sequence of characters, and then your find next, find next, find next would all highlight such any substring that matched that particular definition. They're also becoming much more popular in item-driven games. I use this in Path of Exile because I play games, and Path of Exile allows regular expressions in your stash searches. So whenever you find yourself trying to search for something, you may want to ask yourself, is this regular expression enabled? so that I can search for more complex queries rather than just the exact text string that I put in. Now, I believe I figured out that browsers no longer support this inherently. You may need to download some kind of extension or something of the sort in order to add that functionality to kind of the control F inside of a browser. But that absolutely exists. And if you learn regular expressions, it can save you a ton of time and you look really smart doing it. So yes, Path of Exile allows this. Let's go through some examples just so that we can get some experience with the problem-solving aspect of this. All right, so our alphabet is ABC. So we could define a language that is expressed by this regular expression. What does this regular expression mean? If you were to say this in English.
It does use the terms that you had on the last slide.
Yeah.
The superset of A union B and C.
Yeah. So the star closure of A union BC. Let's see if we can come up with this language. So let's start by just listing some strings that belong to this language. So I'm just going to say something like L equals, and I'm going to start with some curly braces, and we're just going to start listing some strings until we come up with some kind of pattern. And the way that I like to do this is let's start with all strings of length 0. And for the sake of making this a little bit easier, we're going to say that this BC is length 1. So either we have the left side or the right side. So starting with length 0, is there anything of length 0 in this language? Empty string. It's in language, right? Why?
Star closure includes empty string.
Yes, star closure includes 0 of those elements. So it's satisfied by saying no elements of the left side or the right side. If we have no elements of those, then we have the empty string. All right, elements of length 1, either coming from the left side or the right side. This would give us A and BC, assuming that the right side is of length 1. This to help us out with eventually doing this. What about length 2?
A, B, C, and BCA.
So we could have any number of repetitions. So you could put this together, kind of like the reason that I write this L and this R like that is because we can have LL, we can have LR, we can have RL, and we can have RR. So taking this and plugging them into what those actually mean, we can add LL, which is AA. We can add LR, which is ABC. We can add RL, which is BCA. And we can add RR, which is BC. So we can have repetition here, and order does matter. Strings are not the same as strings that have components mixed around. So we continue this process for all L's or R's of length 3, length 4, length 5, length 6, all the way. So this is an infinite language, but this is basically the language that this regular expression represents. Questions about that? Does that make sense? That's one way that I personally like to determine what a regular expression expands into. We can talk about this very similarly to recursion. You could kind of recursively define this left and right side, and then start to expand and recurse, making a bunch of trees of certain depths and how the strings could represent those different strings. How is it similar to recursion? Maybe that's another way to visualize this or to think about it. Let's say we have a tree. The root of that tree is going to be the empty string. What does the left or right branch of this tree mean?
All possibilities starting with either A or B, C.
Yeah. So we could do something like, all right, we're gonna do A, giving us the final string A. We could do BC, representing the final string BC. Then each one of these is going to branch, and we go down the A or the BC, giving us the node AA, giving us the node ABC. So we're kind of recursively defining, we already have this substring, we can recursively define what are we adding to it at the end to kind of expand the remainder of the string. And then we can do a search through this space. Either some kind of breadth first search, if we wanted to figure out length 1, length 2, length 3, length 4, length 5, or a depth first search, although a depth first search of an infinitely deep tree is probably a bad idea. So another way you could think of it, if that makes more sense, given your algorithmic history and the way you visualize problems. So there's also similarity to constructing mathematical expressions. So primitive regular expressions, we can just have null, which represents the language that accepts no strings. Everything is rejected. Lambda, which is the language where only the empty string is accepted. Some character in the alphabet. So whatever the alphabet happens to be, there is a regular expression that denotes each one of those individual characters. Now, we can say that we have R1 and R2, they're regular expressions. We can start with just these primitive regular expressions. Then we can show that regular expressions exist if we union two regular expressions, if we concatenate two regular expressions, if we star closure two regular expressions, and if we put parentheses around any regular expression. All of those denote regular expressions. So we can construct more and more complicated regular expressions out of these components, and then adding those components to existing expressions, manipulating existing expressions, and then allow us to create arbitrarily complex regular expressions. It's very similar to a mathematical expression. You can do and show exactly the same thing with mathematical expressions. We have the same kinds of rules. It's just another expression type. We can define a regular expression string as something that can be derived from starting at any of the primitive regular expressions and applying a finite number of these applications. So if we wanted to do the one from above here, how would we do that? What are the primitive expressions? What are the, basically, how are we creating that from this? kind of want to start with the innermost things and work your way out. So kind of moving to the innermost here, we would have an R1 and an R2 that are B and C. Then we show, since both of these are primitive regular expressions, they're characters in the alphabet. So the alphabet was A and B and C, so both of these are primitive regular expressions, so we don't have to break them down any further into their components. We can show that we can concatenate them together to create a regular expression. So we're going to apply the rule that we can concatenate two primitive regular expressions. Great. Now this becomes the entirety of R1 when we choose this rule, that we can surround an existing expression with parentheses. So we are going to do that. We're going to say that we're going to surround R1 B dot C with parentheses. That's an application of this rule. What comes next? Well, we want to put the star closure on the B dot C. So we are going to do that. We can say now this entirety is R1. So we're going to take the entirety of R1 and add the star closure. Now this becomes R2, because we want to add in an R1 that is a primitive regular expression. We want to add in this A. So this is the A, this is the B, that's right, this is the R1, this is the R2. And we can apply the rule that we can union R1 and R2. So we can do that. Actually, we didn't want to start closure this yet, did we? We start closure the entire thing at the end. Oops. This step didn't happen. Now we can surround with parentheses again. So this is R1, A plus B dot C, surround with parentheses, and then it's still R1. We take the entirety of this and start closure. So it's just a sequence of applications of those rules. The only time you can add something to it is if it's one of these primitive regular expressions, because then you can start to apply the rules to those primitive regular expressions. Does that make sense? Does that process make sense? Just kind of how you would generate an expression. This is useful if you ever have to write a program that does this. You would basically say, these are the rules, here's what you can do. The kinds of problems that I will have you working on in class are mostly you using your brain to come up with a regular expression or something. So you don't have to write the program, but the main application of this out in the real world is writing a program that interfaces with it in some capacity. So knowing how this works is useful for that. Questions? This is a much quieter class than the last one I had. I don't know if that means we're gonna be moving faster. Questions, slow me down, it may be good for you. Okay, so we have some language. We have a regular expression. L of R tells us it's the language that that regular expression defines. We need to, we mentioned this before. This is a regular expression denoting the empty set. It's the no regular expression. We have the lambda regular expression denoting just the set containing the empty string. For every character on our alphabet, we get a regular expression denoting the language containing just that character. Then if R1 and R2 are regular expressions, then we can show the language of R1 plus R2 is just the union of those two languages. Same with concatenation, it's the concatenation of languages. Language of R1 concatenated with the language of R2. If you put parentheses around it, it doesn't do anything to it, it just allows you to do things like define a later star closure. Kind of a grouping. But here's the rule that makes a little bit more sense. If you want to put the star closure here, then it's equivalent to putting the star closure around the language, which is important for generating those more complex expressions where you're only star closuring part. So here's another way that you can kind of recursively do this. The goal of all of these rules is the reduction of some language into simpler components, and you do this recursively. So we want to strip apart a complex regular expression into its components that eventually break down into just the primitive types, these primitive regular expressions. And then these first three rules are the base cases for that recursion. So does that make sense? If you wanted to say, is this expression a regular language? Then you could use a recursive definition saying, all right, here are the allowable rules. I want to derive an expression that's based solely off of these components. So can I break this down into something with just languages of primitives? Which, if it's a regular expression, then yes, you can. Let's go through an example. First, does anyone have any questions? I can show the language and then come back to this slide. That's probably the better way to do it. So here's a slightly different language. We have the star closure of A concatenated with A or B. Go ahead and exhibit it in set notation, which means that we're going to repeatedly apply these rules. So we start with just this, the language defined as this expression. We're going to start breaking it down by the rules on the previous slide. So we're going to apply one of these equivalences down here, and we can use that to talk about this in terms of languages. So you could say this is equivalent to, let's break this apart. Whenever we have a concatenation like this, we set it to concatenation of languages. So we're kind of stripping away this outer parentheses, since that's not necessary. And then we are concatenating two languages together. So this is equivalent to the language of the star closure of A, concatenated with the language that accepts A or B. Taking the A or B, we can apply that rule recursively and say that it's equivalent, that we're going to add a third language into this, to the language of A star. Notice that I added an extra set of parentheses around this. Language of A star, language of A, union language of B. So now it becomes much easier to determine what goes where when we want to expand this into set notation. So this is another way that you could do this. We can now break this down into the language that is the star closure of A. We're then going to concatenate that with either an A or a B. Which gives us this full expansion. So here we have the lambda concatenated with an A. We have the A concatenated with an A. We have the AA concatenated with an A, etc. We have the lambda concatenated with a B. We have the A concatenated with a B. We have AA concatenated with a B. And this goes on forever. This expansion goes on forever, and this expansion goes on forever. So we're just slowly able to break this into its components. And that can give us a much more algorithmic way of defining this. This is useful, one, for your own understanding, but two, if I had you write a program that in general took as input some regular expression. And then was able to write the set expansion of that language. You can imagine writing such a program, being able to do it in general. You would want to code up all of those rules, search through all of those rules for something legal that you could apply until you failed. Then you would verify that each of the elements of that final language expression is some base component. And then you could use those to now go expand in this way and create this as output. So that would be useful for, again, in general, writing a program for it. Questions on this? Thoughts? Maybe a set of thumbs for how much sense this makes? It's hard to tell sometimes if I'm just boring people or if it's confusion. Looks like I'm just boring people. Excellent.
Come on, but
This is not the most thrilling stuff. So just like in math, we need rules to avoid ambiguity in our expressions, because we get things like, all right, without ambiguity and without precedence, we get ambiguity like A concatenated with B union C. What does this mean? We put the parentheses around basically AB union C? Or do we put the parentheses around A concatenated with B union C? These are different languages. Does that intuitively make sense that these are different languages? They represent different sets of strings. Here, there is only we have the possibilities. Here, AB is in the language and C is in the language. Here, AB is in the language, but AC is in the language. So different languages. So the precedent rules we're going to state is that we first do star closure. After we have resolved star closure, we will resolve concatenation. After we have resolved concatenation, we will resolve union. It's nice that they use dot and plus to represent concatenation and union because it's consistent with what we are used to from our own mathematical expressions. Times has a higher precedence than plus, so the symbol that we use for times representing concatenation has a higher precedence than the symbol we use plus for, which represents union. So it doesn't actually change the typical order of operations that you've worked with in mathematical expressions forever. And as I've been doing already, just like in math for multiplication, if there is no dot, that just means it's there. It still means concatenation. So R1, R2 is equivalent to R1 dot R2. All right, time for some practice problems. You've been sitting here listening to me long enough. All right. So we're going to find in set notation, what language does this expression denote? See if you can come up with some kind of the language of this regular expression equals or is what set? Show me some kind of set notation expansion of the strings that would be in this language. anyone found a good way to represent this yet, or to start drawing it out? Because obviously this is infinite in kind of multiple dimensions. So sometimes I find writing out set notation, at least before I combine it into some adequate set notation, to start drawing this out in multiple dimensions. So we have kind of a left-hand side that is broken down into a left and a right. And this is all a left. And then here we have a left and a right inside of the right that is this right-hand side. But because this has a star closure, we can repeat this an arbitrary number of times before we even start that. So I'm going to do some kind of two-dimensional representation of this, kind of drawing it out as a matrix. Because I find that that just makes more intuitive sense to me, and that might make more sense to you as well. So we know that we can, basically, we're gonna hold this constant. This is all going to be an A, and we want to only do elements of 0 or more of these. I don't even know if that makes sense. This is kind of a nasty problem. So, all right, we want some way of breaking this apart into those components. So we can repeat this left an arbitrary number of times. Let's just start with 0 times. What can we do if we repeat this 0 times? So this part would be that, but we still need to concatenate that empty string from this, because lambda would be part of this. Lambda concatenated with one of these two things. So if we do the left-hand side 0 times, we end up with A, and we end up with BB. Those are both in the language. So this is 0 repetitions of this. The next row that I do is going to be 1 repetition of this. So now we have L to the first R. So what are all of the possible strings with 1 L followed by 1 of the R's? Well, first of all, how many of them are there going to be? Before we start listing them, we need to know when we're done. So how many are there? I believe there are 4. So we need to now break this down into repeating this once, followed by the left. This once, followed by the left. This once, followed by the right. This once, followed by the right. So we end up with, here, we end up with AA, the left, left. We end up with LR, A, B, B. We end up with RL, B, A. And we end up with RR, B, B, B. Great. Now we want 2 repetitions of the left-hand side, followed by 1 of the right-hand side. How many of those can there be? Yeah, that's 8. So I'm gonna start, instead of having this as L and R, I'm actually gonna make these lowercase, just so that we can. So this is the, how do I do this? LL, LR, RL, and RR, maybe. As a way of combining this. So now if we have 2 from here and 1 from here, then we have LL, LL, RL. We would have LL, LR. Let's do the L1 first. L, R, R. L, R, R, L. Now we can start the writes. L R L L L R. Right, those become your 8 combinations of that. We kind of have 3 variables that we need to repeat. So this becomes the superset of that. We end up with 2 to the number of elements that this is, which is 3, so there should be 8 of them. Again, from that very first lecture. So if we wanted to list these out, this represents A, this represents that same A, this represents the A. So we end up with A. We end up with A's, B. We end up with A. We end up with A, B. We end up with B, A. B. See, done 5. So B, where is that? Did I miss one? Yeah, I just going in, that's BAA. Let's go back to count, there are 6 of those. So this is now B, and this is BBA. That's why. A and B. There we go. So that's row 3. So now if we've identified this as the pattern, now we can kind of continue this pattern infinitely. So if you were trying to do this and define this in terms of actual math, you would have some way of showing what does this first row represent? What does the second row represent? How do we come up with a mathematical expression, and how do we show this continuation? Again, this is a little bit outside the scope of the class, but it's worth at least showing how you go through that expansion process, because you will find in some application of what you're doing eventually, you want to be able to do something like this programmatically. So it helps to have some kind of notation that you can use to break this apart, come up with this, come up with that, and then feed that as instructions into whatever program you're writing or using. Questions on what I did or how that works? You may have an arbitrary number of components or variables. Questions before it goes away? Does it make sense? Please do raise hands and clarify if anything that I did is not clear.
So for the answer for this, like what would you want the answer to be? Just to write all that out?
Yeah, I would just write something like this as a way of showing this. It's a little bit outside of where I expect people to be right now to come up with a mathematical formulation for exactly what this is in language, but you could think about what that might look like. Because that would be the nice shorthand way to do it. If it were in a paper or a textbook, it would be in that nice short mathematical way, which is very annoying if you're trying to understand how something works, which is why I always go through this process. Because I feel like this is much more useful to people than a single mathematical formulation, because it's really show how you get there. If you can explain how to get there and don't have the shorthand, that's better than having the shorthand without the explanation. So I prefer to pause here. Just some way of denoting some algorithmic process for enumerating all of these strings in the language. That's the kind of the computer science version of the shorthand mathematical expression. You would only need that shorthand if you were writing it in the paper. Let's try it again. Note that now I'm asking for an English description of this language, not a set notation description. Note that I don't want a technical English description. I don't want the star closure of, that's not an English description. That is a automata theory description. So come up with an actual English description that a third grader might be able to understand. Yeah,
Would be an even number of A's followed by an even number of B's followed by a B,
could you shorten that?
followed by an odd number of B's.
Yeah. An odd number of beats. So because this is optional, we know that there's at least one of them. And one is the first odd number. So exactly right. And this would be the set of all strings with an even number of A's followed by an odd number of B's. As you start getting more and more tools under your belt, it becomes very easy to over-describe the complexity of something. If you can describe it such that a third grader can understand it, then you probably should. That just becomes a nice way of communicating with the outside world as you get more and more skills. All right, so write a regular expression for this very informal description. The language is all strings W in the alphabet over binary such that this string W has at least one pair of consecutive zeros. But note, yeah, okay, that's fine. Just one pair of consecutive zeros, at least one pair of consecutive zeros. This becomes a little bit more complicated. So now your goal is to come up with the regular expression. So you're able to use plus to represent union, concatenation, star closure.
They're okay for if you have a grammar for something, you can follow like some algorithm to get the regular expression for it.
Yep.
Okay.
There are conversion algorithms for every formality. So yeah, we'll be going over grammar to automata and automata to grammar. Not so much the regular expressions into those things, but those do exist. They're just a little bit more technical. You have an answer? You have an answer that we're happy with? Couple of solutions for people. So let's take a look at, we know there has to be a 0, 0 somewhere. But what comes before that And after that is arbitrary. So how could we define a sub-expression that says arbitrary? Any thoughts on what that could be? What does a sub-expression that says an arbitrary number of zeros or ones? So arbitrary could include zero, but I think we want to consider the star closure. I guess, yeah, we are out of time, aren't we? But we end up with something like this, where we say the arbitrary here can be 0 or 1 star. It says there could be 0 of these, we could choose 1 of these, we could choose 2 of these, and we need to surround the 0, 0 with 1 or the other. So this can, the arbitrary can come before, the 0, 0 has to happen. This can come after. Is this the final solution? What if there are multiple 0, 0s?
Would that be before the star closure?
Yes, yes, it would. So that's why this is the right answer. We'll come back at the start of tomorrow's class and get some last practice with us before we dive into regular grammars. I apologize for how lecture heavy this class was. I try to not do that too frequently, throw in more practice problems. There will be a lot more practice tomorrow. Exam is Friday, homework is due Wednesday. I have office hours starting right now. If anyone has any questions about either of those. Study guide is on campus. Thanks, everyone. See you tomorrow.